So today we discuss the electric charge and field one-shot revision video. Okay, here we discuss the summary of the each and every chapter of class 12 board exam. Okay, the first chapter is electric charge and field. Okay, so what is electric charge? So there are two types of charge. We know that. Okay, that is a one charge is a positive charge, other is a negative charge. There is a two types of charge. Okay, so here another properties of charge is a conservation of charge. Conservation means charge can neither be created nor destroyed. It only transfers from one body to another body. The total charge of an isolated system is really constant. Okay. So next, the quantization of charge. So what is the quantization of charge? Any charge Q is an integer, the multiple of the fundamental of unit charge. So what is the fundamental of unit charge? That is E, the small e, that is equal to 1.6 into 10 to the power minus 19 Coulomb. Okay, the charge of a proton or say that a proton or electron. Okay, so that let's come to the whiteboard and the chapter 1. Okay, electric charge and field. Fields. Okay. Just discuss a revision class. Okay, so we know that there's a two types of charge. Okay, one is a positive charge, other is a negative charge. Conservation of charge. Okay, so second is a conservation of charge. Means charge is neither created nor destroyed, transform one body to another body. Next, the quantization of charge. So quantization of charge means that any charge. Okay, suppose there is any charge, say Q, that's any charge. Okay, as an integral multiple of the fundamental unit of charge. Okay, so integral multiple of fundamental unit of charge. There's a integral multiple of fundamental unit of charge. Okay, so that is there is a n. Okay, so n 1, 2, 3, or suppose minus or minus 2. So okay, that's a n plus or minus, and there is a e. Okay, so what is a e? Small e, small a is the charge of an electron or proton. Okay, so what is a e? Is a charge of electron or proton. If electron means a minus, proton means a plus. So final expression we get that is equal to Q, that is equal to plus minus n times E. Next is additivity of charge. So additivity of charge means the total charge of a system is the algebraic sum of all individual charges. Just simple algebraic added here. So that's the additivity of charge. So number 3, the additivity of charge is a total charge of a system. Total charge of a system is the algebraic sum. Is the algebraic sum of all individual charges. Of all individual charges. Okay. Next point is there is a conductor and insulator. That's a very important. What is a conductor and what is insulator? Number 4 point, conductor and insulator. Okay. So what is conductor and what is insulator? The name suggests a conductor means a good conductor of electricity, mainly there is a charge, there is a metal Actually, conductor means a metal. Okay, there's a allowed to flow of charge between them. That's called a conductor. Allowed to flow of charge. Allowed to flow of charge is called a conductor. So what is the insulator means? Do not allow to flow of charge. Okay, that's the basic some properties of charges. Okay, now next point is a Coulomb's law. Next important point in this chapter is Coulomb's law. Okay, so Coulomb's law describes the force of attraction or repulsion between the two stationary point charges. Keep in mind here the charge are in stationary. Okay, the charge are in stationary. Okay. Charge are in stationary. Okay, so there is a force of attraction or repulsion between two stationary point charges. Okay, so here two stationary point charge, suppose you describe that is a one charge is plus q1 and the charge is suppose minus q2. So the formula, so there is a force, so there is a force. Okay, so they are unlike charge, so there is a force of attraction here. So this force of attraction is in that direction and q2 in q1 direction, towards q1. q2 force is towards q1 and q1 force on q1 due to q2 direction towards q2. So that is a f1 due to 2, that is f2 due to 1, and they towards each other because they are unlike charges. There is a force of attraction. So this force, Coulomb's law states the force, that is F, okay, and that is equal to 1 over 4 pi epsilon naught. There is some constant. So 2 charge, multiple of 2 charges, Q1, Q2, we consider only their magnitude by their separation square. If the separation is R, so that's a R square. That's the Coulomb's law. So R is the distance between two charges. So here we get there is some constant. These are the constant 1 over 4 pi epsilon naught. Okay, and the constant value, that is suppose say that is a k, some constant, that k that is equal to 1 over 4 pi epsilon naught, that is equal to 9 into 10 to the power 9, and the unit is Newton force meter square by Coulomb square. That's a constant. Okay, and the SI unit of that constant. So if there is a force, obviously there is a vector term. So vectorically, if I check that is a force is a vector. So this force F1 2, okay. So 1 over 4 pi epsilon naught. That epsilon naught is a permittivity of free space. This epsilon is called permittivity of free space. Okay, that is some q1, q2 magnitude only. Now the r is a displacement vector here, so r1 2 direction, okay, the square, and r1 2 cap, and f21 both magnitude be the same, 4 pi epsilon naught, q1 q2, here is r21 square, r21 cap. The direction here different, otherwise that the magnitude be between these two forces, there is a Newton and these two Newton be the same. That's a force. Okay, that's the basic of Coulomb's law. And here that is some constant, okay, and the permittivity of free space. Remember the value that epsilon naught, and this value also given in question paper. Okay, Otherwise you know that is permittivity of free space. The value is 8.854 into 10 to the power minus 12. The SI unit is that epsilon not here, that is Coulomb square, okay, times meter to the power minus 2 per Newton. Now here is another important is the principle of superposition. So here you see that what is the principle of superposition? You see that there is a two charges, Q1 and Q2. If there is a more than two number of multiple charges here in the system contain multiple charges. If system contain multiple number of charges, here we apply superposition principle. Superposition principle. Okay. So superposition principle say that the net force on a charge due to multiple of other charges is the vector sum of the individual forces. Okay. So basic the algebraic sum here, and so that is a net force or total force, that is a individually force we added here, F1, F2, or say the F3. If there is n number of charges, so that is a Fn. Okay. So the net force on a charge due to the multiple of other charges is the vector sum of the individual forces. That's the superposition principle. So these are basic algebraically added. Okay, that's very important. Next important point, and that is the electric field. Or you can write the definition of superposition principle. So I write down here for the video, and if you used to write, then write. Okay, the net force on a charge due to multiple other charges, due to multiple of other charges is the vector sum of individual forces That's the definition of superposition principle. Now here the another important concept we learn in this chapter, that's the electric field. That is electric field. What is electric field? Electric field is a region. Electric field is a region around the charge where its electrostatic force can be experienced. Okay, so electric field is a region. Okay, around a charge where its electrostatic force or Coulombic force, or electrostatic force or electrostatic force can be experienced. Okay, so that's the formula. So here we say that is the two charges here. So calculate the field around this Q charge. Now bring a test charge. Suppose a positive test charge. There is a small value of Q. Keep in mind there is a test charge. So field. Okay. So there is a force. Obviously, if a force, if they are in positive charges, so like charges. So that's a repulsive force. That is a F. And these and separation we say that R. So here there's the electric field, that is a function of R, that is equal to force, this force, the electrostatic force on Q1 due to test charge, F of R by test charge Q. That's the test charge there. And this electric field is a vector field. This is a vector field. That's why vector sign is very important. Okay. So what is the SI unit of that electric field? So very easy. That is Newton per Coulomb. That's the SI unit. Okay. And this is a vector quantity. Okay. So Newton per Coulomb. So what is the electric field due to a point charge? That is simple. Okay. And that is the electric field. Finally, we get the expression ER, that is equal to 1 over 4 pi epsilon naught. Okay. So we know the force, that is a capital Q small q by r square times 1 by r 1 by q, sorry, 1 by q, and the reaction is r cap. This will be the cancel, and you get final expression, that is 1 over 4 pi epsilon naught capital Q over r square, that is the r cap, that is E vector. Okay, that's the expression of electric field. Okay, there is a direction, obviously keep in mind, away from Q if there is a positive, and towards the Q if is negative. Okay, so keep in mind, if the test depending on positive charge, if there is a negative charge, so test charge with a positive, so we know that actual repulsive force depending on the polarity of the charges, or attractive force or repulsive force depending the polarity of these two charges. Now another important point is electric field lines. Electric field lines. Electric field lines. So what is electric field lines? Electric field lines is an imaginary line. Okay, imaginary curved tangent which at any point gives the direction of the electric field at that point. Okay, so what is the electric field lines? Okay, that's the imaginary curves. The imaginary curves, imaginary curves line. Okay, imaginary curves line, and obviously there is a tangent. Remember, there is a tangent uh, to which at any point gives the direction of the electric field. Gives the direction of the electric field. Of the electric field. That's the field line. Okay, field that point. That point. At that point. Okay, so there is some properties of electric field lines. So here some properties are properties number 1. Okay, start from positive. So start from electric field line, start from positive and end towards negative. Okay, positive to negative, the directional property. Start from positive charge and end at a negative charge. Okay, number 2. Okay, never intersect. Never intersect. Because if they intersect, suppose if that is a field electrically at that point, that is a tangential. If they intersect, so at that point, if say that is a intersect, so here you see that tangent at that point in that direction, tangent at point in that direction. So one single point have two electric field. That is a very impossible. So that's why they do not intersect. And number 3 point. So density of field line is the proportional due to the magnitude of the electric field. Okay. So density of field lines is proportional to the magnitude of the electric field. So density of field line. So density of field line. So rho represents the density of field lines. Field lines is proportional to the magnitude of the electric field. the magnitude of electric field. Okay, and number 4 point number 4. So they are continuous curve without any break. So they are continuous. So no breaks here. Okay, that's why they are a continuous. Okay, so they are continuous. And number 5th point and the last point is they do not form closed loop. They do not, or the T obviously do not form closed loop. Okay, that's the 5 point. That's very important. Okay, for short question. Now, next point we discuss next concept, that is a electric dipole. That concept is electric dipole. Dipole. Okay, so what is a dipole? There is a two pole. Okay, two pole means there is a two charge. So system has two equal and opposite charges separated by a small distance. So two equal magnitude of charges. So one is plus, so other one is a minus. The plus q, there is a minus q. Okay, so there is separated by a very small distance. Suppose that distance is, say, that is r. Say that, or you say that uh, any other values. Okay, so here the dipole moment. So that important. There is a vector form. This is called dipole moment. Dipole moment. That is a p. Obviously, there is a vector. Okay, that is equal to charge. Okay, q times and this r. Okay, so and the distance between two charge, and keep in mind these are a vector. Okay, dipole moment is vector, so vector means there is a direction. Okay, very important. Minus to plus direction, dipole moment moves minus to plus direction. Okay, so negative charge to positive charge, so that's a p, that's a vector direction. Okay, so SI unit, what is the SI unit? SI unit, unit is very easy. There is a Q stands for Coulomb and R is length, so that is a Coulomb meter. That is the SI unit of the dipole moment. Okay, now here is some calculation. The calculation here, I skip that calculation because there is a review class. Okay, if you want to check that for full calculation here, so we play, there is another playlist here. You see that playlist, there is a full lecture here. Okay, so that lecture we solve this. Okay, here I'll discuss only a one shot video or summary class here, you can say that. So there is a calculation here. So calculation is there that a field, first the field on axial line, end on position, position. So here the axial line, that is suppose that E, okay, that is equal to 1 over 4 pi epsilon naught, that is equal to twice P, obviously a vector, by R cube. Obviously there is a vector, so there is E and there is a direction is P, minus to plus direction. There is an axial line. Okay, so the direction parallel to the dipole moment, and the direction parallel to the dipole moment. Okay, that's a very important. So there is a field means here, that's the electric field, and that part B, another point. Okay, field on equatorial line, field on equatorial lines both side on position. On position. Okay. So the final expression is that uh, so E, obviously there is a vector, that is 1 over 4 pi epsilon naught. There is a dipole moment P, obviously the vector, that by R cube. Okay, and here these 2 points obviously. Okay, and these are the R. Okay, keep in mind these are the R, and if you see the diagram, actually the diagram is look like this. So there is a charge, suppose a charge plus Q, and there is a minus charge plus minus. Okay, and say that the distance is, suppose these two charges twice A, that's the dipole center. So here that electric field at that point. Okay, that point electric field here, these are on due to the axial line, these are called. Okay, and these are length p that R, and here this condition is R, obviously these are much greater than twice A. These are the axial line, and what is that equatorial line? So there is a two charge, obviously the plus charge Q, there is a minus charge Q. Okay, obviously there is a P in that direction, that's a dipole center. Suppose okay, and this length P. Okay, electric field in that direction. Suppose okay, that's a R. Obviously this length be the twice A. Okay, that's the dipole center, and that's the dipole moment vector, minus to plus direction. That's the dipole moment P. Okay, that's the electric field at that equatorial plane. Here, actually, there is a plane is look like this. There is a plane here. Okay, P in that direction and electric field opposite direction. So that's the anti-parallel, but they are in parallel, but direction is opposite here. So here, keep in mind the field at at an axial point is a twice of field of the equatorial point at the same distance. Okay, and you see that here is a, keep in mind the nodes. See that these equation very carefully, and if a equatorial line, so axial line, that is equal to 2 times 2 into equatorial line. Okay, so axial line electric field on axial line is a double of that electric field equatorial line. Okay, the field at an axial point, the field at an axial line at an axial point is twice the field at an equatorial point at the same distance, at the equatorial point at the same distance. Okay, so now here we discuss that another point, another important concept here, that there is a dipole in an uniform external field. So discuss dipole in a uniform external field. So dipole in an uniform, so external field. So obviously there is an uniform external field. Okay. So experience a torque but no net force. So here experience a torque, that is equal to tau, and that tau equal to the vector that is equal to P cross E. Okay, or say that is a PE sine theta. Okay, the torque is a rotating vector. So now there is a potential energy, that is U, that is equal to minus P dot E. So if there is a rotation, so that's why the tau, and there is a cross product because the tau is a vector and energy is a scalar. So that's why a dot product here. So that is equal to minus PE. So in case of what is the due to PE cos theta, and say that if some state of equilibrium here, state of equilibrium, say that stable equilibrium, for stable equilibrium, for case of stable, so theta be the 0 degree, so potential energy here cos 0 be the 1, so that is PE. And is a for unstable equilibrium, that theta that is equal to 180 degree, that is U equal to minus cos 180 be the minus 1, so that is minus 1 plus, that is plus PE. Okay, so here in case of that is a cos 180 degree, that means energy be the maximum here. Okay, energy be the maximum here, and P and E are anti-parallel, and in the 0 degree, so there is parallel, and that is a minimum here. Okay, now next electric flux concept. So electric flux, phi, or say that is phi E, the electric flux. So number of electric field lines passing normally through a given area, that's the electric flux. So definition of electric flux is the number of electric field lines, the number of electric field lines passing normally through a area, passing normally through a given area. A given area, that's the electric flux. So that is flux phi, that is equal to E dot area is A. Okay, so flux is a scalar quantity, that's E dot A. So finally get it, that is equal to EA cos theta. Theta is the angle between E and A. A is the area vector. Okay, so now, so here, so for general definition, so phi equal to integration, that is obviously closed integral here because the surface is a closed surface, obviously, that is E dot dA. So the SI unit is, so the SI unit of flux, so that is equal to, so electric field, so from electric field that is equal to electric field, that is Newton per Coulomb times meter square. So next concept is we discuss, that is the Gauss's law. That's very important concept, Gauss's law. Gauss's law. Okay, so what is a Gauss's law? So Gauss's law states that total electric flux through a closed surface is equal to 1 by epsilon naught times the net charge enclosed by the surface. So definition is very important for Gauss's law. So the total electric flux, the total electric flux through a closed surface, through a closed surface is equal to 1 by epsilon naught times the net charge enclosed by the surface, enclosed by the surface. That's the Gauss's law. And the expression we get for, that is equal to phi flux, that is equal to, we know that that is E dot dA, that is equal to Q enclosed, okay, times 1 by epsilon naught. So here is some key point. You remember that a key point very important here. The surface is an imaginary Gaussian surface. The surface we choose, that's obviously imaginary Gaussian surface. Next point, the flux depends only on the net charge. Net, obviously their charge is enclosed. Okay, that's enclosed charge by the surface. Okay, and third point, it is used to calculate electric field for highly symmetric charge distribution. The very important key points here for Gauss's law. For key point, first key point is the surface is an imaginary Gaussian surface. The surface is an imaginary Gaussian surface and 2 point, the net flux depends only the net enclosed charge. Only on the net enclosed charge. Okay, that is Q enclosed. Point number 3, there is a key point very important. It is used to calculate. It is used to calculate electric field E. So Gauss's law helps to find the electric field, okay, for highly symmetric charge distribution. For highly symmetric charge distribution. Okay, that's the key point. And here another point to discuss here, that's the application of Gauss's law. That's the very important. The application of Gauss's law. Application of Gauss's law. Okay. So here we discuss just outline or summary here. The first application is the infinite long straight charged wire. Infinitely long straight charged wire. Okay, so here, so there is charge density, that's called lambda. Lambda is the linear charge density. Linear charge density. That is equal to, okay, that is a total charge by some length. Okay, that is a linear charge density, and the unit is a Coulomb per meter. That's obviously SI unit. Okay, so here the electric field. So here we get electric field E for linear charge density, that is equal to 1 over 4 pi epsilon naught, okay, times twice lambda by R. Okay, so here you can simplify these two, cancel these 2 and 4, 2. So you get 1 over 2 pi epsilon naught times lambda by R. 1 by 2 pi epsilon naught times lambda by R. And the important point is direction. Very important, that is a direction. If there is an electric field, obviously this is a vector, so obviously there is a direction. And the direction is the important, radially outward. If lambda is positive, the direction is outward. Suppose there is a charge, positive charge here, so obviously electric field is outward. If the charge is negative, so electric field always inward. Okay. Now, the second application is the infinite plane sheet of charge. Second application is application number 2, uniformly, sorry, 2, infinite plane sheet, right, plane sheet of charge. That's very important. So here, first point, okay, the surface charge density, here, surface charge density, that is we get sigma, that is obviously Coulomb per meter square. There is a surface, that's why there is a meter square. Previous there is a line, so that's why meter. Now there is a Coulomb per meter square. Okay, so another point is the electric field, that is electric field we get sigma over twice epsilon naught. Okay, so third point is the direction. Okay, first, second, third is the direction, and direction is perpendicular to the plane away from it. If the sigma is a positive, and electric field is perpendicular to the plane or surface, plane, okay, away from it. And last and important point, field is uniform. This is the field is uniform. Okay. Now the last application, uniformly charged thin spherical shell. Last point, point number 3, application obviously. Last application is uniformly charged solid sphere. Okay, so here some point. Okay, so point is charge q. So radius of sphere, that is capital R. Now we first consider is outside, calculate electric field outside of the sphere. Now we choose a Gaussian surface of the radius beta r is greater than capital R. Now that electric field obviously, that is E equal to 1 over 4 pi epsilon naught q by small r square. Okay, that's the electric field. Okay, is the outside. Now here the inside, or suppose on surface. First discuss the on surface. On surface means that is small r equal to capital R. Here the on surface, so the electric field E, that is equal to 1 over 4 pi epsilon naught. Okay, so here the on surface, that is q over capital R square, because the Gaussian surface, and in the actually there is surface, okay, R square. Now what is the inside of the sphere? Now that's the inside. So inside, small r is less than capital R. Now this Gaussian surface encodes the zero amount of charge. If there is zero amount of charge here, okay, so that is electric field with a zero here. That is the application of Gauss's law. Now here for final tips, final revision, what is the important in our first chapter? Okay, they must know the derivation. That's the point, is must know derivation. This is a very important here. Derivation. The first important is that electric field on the axial line of the dipole, electric field on the axial line of a dipole. Second point, electric field on the equatorial line of a dipole, electric field on the equatorial of the dipole. Third, torque on a dipole in a uniform electric field. Fourth point, that's a very important key point, application of Gauss's law. Application of Gauss's law. Okay, the 3 point is very important. Infinite long state charge wire, an infinite plane sheet of charge, a uniformly charged thin spherical shell. These 3 applications is very important for derivation. Okay, the must know derivation is very important. Okay, now final is, and the last is quick formula sheet. Okay, last point discuss, that is quick formula sheet. Okay, first the Coulomb force, that is equal to F equal to K Q1 Q2 by R square, K equal to 1 by 4 pi epsilon naught. Number 2, electric field, that is equal to F by test charge. Number 3, E on dipole, axis, that is E equal to K 2p by R cube. Number 4, E on dipole equator or equatorial plane, on dipole, that is E equal to K p by R cube. Number 5, dipole torque, that is equal to Pe sin theta. Number 6, the potential energy, that is minus P dot E. Okay, electric flux, that is phi equal to Ea cos theta. Number 8, Gauss's law. Okay, that is phi equal to Qn close by epsilon naught. Oh, sorry, that's the phi equal to. Okay, that's the phi equal to. Number 9. So here the 3 application of Gauss's law. First, for electric field due to wear line, or choose a wear, that is equal to E equal to, okay, K2 lambda by R for sheet of paper. Okay, for 2D, that is a E equal to sigma by twice epsilon naught, and sheet of paper. So here is only surface 2D. Here is surface. And third and final is spherical shell for outside. Shell outside. Okay, that is E equal to KQ by R square. Okay, that's our basic Gauss's law and their application. Okay, that's the summary class. Okay, the first chapter, electric charge and field. Okay, so if you have any doubt, please ask in comment section. I will try to give the answer. Okay, so next class we discuss the next chapter review. Okay, these are the, keep in mind, these are the summary class. Okay, not detailed in class. Okay, here these are key point, only discuss the key point here for revision purpose, not for conceptual purpose. If you want to clear the concept of these are all topics. Okay, so that's a separate video, separate lecture series here. You click that lecture series. I pin that lecture series in our description button or I button. You see that lecture series. That's very important for understanding the concept. Okay, you see the lecture, and if you have any doubt, please ask in comment section, or if you wish to mail me. Okay, I will try to give the answer. Okay, so today in the class here. Okay, thank you for your time.